Welcome to our fourth lecture on solar electric energy systems. Today we will talk about manufacturing of solar modules, their characteristics and their performance. So first, make a definition of what's a solar module. So last lecture we discussed about the manufacturing of silicon and of solar cells. Now we interconnect these these cells into a string. So we interconnect them in series. So all the voltages of the solar cells are added. The current remains the same. That's an important fact because the cell with the lowest current defines the total performance of the string. So usually we saw already in the manufacturing video that the cells are sorted, and they are sorted to have an equal current. And these are put together in strings and modules, all cells with an equal or within a certain range, equal current or short circuit current. And so you'll find, if you take a look at some brochures, you find modules with different power values, which look pretty much the same. This is due to the sorting. So you'll find modules with 390 watts, 395 watt, 400 watt, and 405 watts, and so on. This is due to the sorting, this serves to avoid losses caused by single cells, which may block the total current of the module. So these strings are interconnected to a so-called solar matrix, and this matrix is encapsulated within a solar module. And this usually, formerly they had about 50 watts, and then the power increased to 100 watts and 200 watts, and nowadays 300 to 400 watt is the standard. If you need higher power outputs, you interconnect those solar modules to a so-called solar panel or a photovoltaic generator. Usually you interconnect them in series up to the maximum permitted voltage, which was formerly about 600 volts DC, was increased in the last years to 1000 volts DC, and the newest modules have the maximum permitted voltage of 1500, and even there are some prototypes which permit 2000 volts. And then if you need even more power, you start to interconnect these generators in parallel. We see that later when we arrive at that part. So here you see the interconnection of the cells here. This is then carried out via cell interconnectors. For example, here these are thin copper flat wires, you do this soldering, and we see some picture of it, and this is the matrix soldering, the lamination procedure, and almost at the end we put the terminal box there and the frame, and at the very end we do some testing to see what's the IV characteristic, the short circuit current, the open circuit voltage, and most important, the power of that module. And then it goes to the sale of the module. Here we see a cross-section of the module. So you see the solar cell matrix, or the different strings interconnected together. Then we have an encapsulant, the EVA sheet. This means ethylene vinyl acetate, and top of that we have the glass. Sometimes even below there's glass, so-called double glass modules, but most of the modules are still made with a backsheet foil, which is some polyester or Tedlar lamination here, to avoid humidity to enter the solar module. Here we see the effect of the interconnection of solar cells. So this is compared to the other IV curve, which was at 1 volt at maximum. Here we have 5 volt as maximum. So here the IV curve, especially the voltage of a single cell, is very small here. So that's the IV curve of a single illuminated solar cell with maximum voltage of about 0.6 volts. The current is in full scale, so we have here on this particular cell a current above 4 amps. Many high efficiency solar cells or large solar cells, they have currents up to 16 amps. And now you put them in series. That means the current stays the same and the voltages add up here. For example, if you look at number 2, these are 35 fully illuminated solar cells interconnected in series here. So we have the add up all, so it's 35 times 0.6 volts. And last but not least, we see a 36 illuminated solar cell. So this is the final the final IV curve for solar modules with 36 cells. Nowadays, modules are even have 72 interconnected solar cells. Here again, we see the cross section with the glass, the interconnected solar cells. Here the stripes are quite straight. Usually you apply a bow here to make it possible that the solar cells can thermally expand, because they have a different thermal expansion coefficient than the EVA or the glass or the backsheet laminate. So you allow the cells to expand at a different rate than the rest of the laminate. Then you have here the string interconnector. Usually that's not directly at the ceiling, it's a bit apart from the frame to allow a good insulation. Remember the latest modules have a voltage of 1000 to 1500 volts, and so they have to be kept a distance to the metallic frame. So here another 3D representation of a laminate. So you see the solar cells, the EVA sheets. So quite interesting kind of plastic. Usually if it's raw, it's semi-transparent. If you heat it up, it's a copolymer. It gets transparent and it stays transparent, and you cannot melt it again like a thermoplastic plastic. So once melted, you can't do anything anymore. That's a bit problematic for the recycling procedure. You virtually have to burn it to get the cells out of the laminate. The thermoplastic laminates either have a poor durability or they are very costly, so they are only seldomly used. So we have the glass here, vicinity of 4 millimeters, and then we have the ceiling and the frame. Since a couple of years, even a highly hardened glass with a thickness of 2 millimeters only on the market. And here you see the backside, number 6, Tetla polyester foil on the back sheet, as I mentioned already, that serves to protect against humidity. Here you see just the cells, as I mentioned already. They are put together in different boxes here to put together in a single modules, because they should always have about not the same power, but at least the same current, because the entire current goes through each cell, and if you have cells with different currents, they may block the performance of the entire module. Here you see the fixing of the interconnection stripes. And here sometimes, depending on the machine, there could be also some damage, so you have always to have replacements and so on. Even nowadays, that's often done manually. Here you see the soldering of the strings together to the so-called solar matrix. The right side, you see the soldering of the matrix together, and here you see some stripes going to the terminal box at the end. The terminal box, you often find the bypass diodes and the interconnectors. Here you see a matrix. This is a factory in Indonesia in 2010, which where also the manufacturing is doing manual. It's from 2010, as I told you. It's hard to take photos nowadays in solar factories, but in general, the process is the same. It's even more visually attractive. These old photos nowadays you don't see a lot because it's covered by masonry. Here you see the application of the EVA foils. As I told you already, these are semi-transparent in the beginning, and after the lamination process, they are getting totally transparent. Here you see just a laminator. The lamination has to carry it out in a certain pressure temperature profile, which is shown here on the right part. There are different kinds of EVAs, normal cure EVA, fast cure EVA, or super fast cure EVA. It means the curing of the copolymer carried out in different speeds. Sure, the super fast cure EVA is most expensive, but on the other hand, you can produce more modules per hour within a module, within just a module factory. Typical temperature is around 156 degrees, and curing is about in 10 minutes. Sometimes you take them out of the laminator and they cure on their own in a curing room. And at the very end, you apply the fixing of the frame. Nowadays, it's made automatically. In 2002, this was still carried out manually. Here you see the fixing of the edges. And we have the final module after the attachment of the terminal box. On the left side, you see a single crystalline modules. On the right side, you see, maybe you hardly see the monocrystalline structure, the multicrystalline structure on the right side. So SC means single crystalline, MC means multicrystalline. And here you see the data sheet here on the module, and you see here power under maximum power. In the maximum power point, you learned already what that is. So this was during that time, it was 165 watts. As I told you already, nowadays within it, the power of a typical high-grade solar module is 400 watts. There is a tolerance plus or minus 3%. This is a bit critical for the financing of the solar power plants, because usually the bank, they don't want to take any risks, so they take the worst conditions, so they always take minus 3%. So after, in the last decades, the module manufacturer started to make it minus 0% and just have positive tolerances in order to keep the good financing conditions. So if you have, for example, nowadays a 400 watt modules, you are quite sure that it has at least 400 watts under the standard test conditions. So we have here also the voltage under maximum power point condition, and in the maximum power point 35.4 volts. The open circuit voltage is surely a bit higher, which is here 43.3 volts, and the short circuit current is here 5.05 amps. It's not given the current and the maximum power point, so but it's easy. Just you divide the power of in maximum power point by the voltage, and then you automatically have the current in the maximum power point. Similar on the right side here, you have also here a data sheet and just some seals whether the modules has been tested and certified by an entity. In this example, it's by TÜV. Here you see the structure of a monocrystalline, multicrystalline PV module. Here you see thin film modules on the left side made of amorphous silicon. So you see here the size is quite big. So this is almost 2 square meters, and the power output is relatively small, 120 watt only. That means the efficiency is really poor of that, and this is the reason why it's almost not used anymore nowadays, because with 2 square meter nowadays you almost get a 400 watt module. The architects still like it a lot because the structure is very homogeneous, but in general, from the cost-benefit ratio, they are not very much used anymore. On the right side, you see a cadmium telluride module. Remember the green line when we take a look at the spectral efficiency. So the spectral efficiency was quite good. Also, there were some improvement during the last years in conversion efficiency. So the latest announcement are that they are in the vicinity of 18% for the production modules. The only problem at these kind of thin film modules is the use of cadmium and telluride. It's thin film only, but still you have to think about the recycling, because cadmium is a hazardous material. Also telluride is not as cheap as silicon. Here you see a crosscut of such a cadmium telluride solar cell or solar module. Due to the thin film technology, pretty much the same. It's kind of integrated. The cells are not cannot be separated from the module. Here is the setup. So this is where the light comes in. This is a glass, and then you have a TCO film. This means transparent conductive oxide. So instead of contact, you have a kind of oxide. This is usually worse than a real metallic contact because they degrade easily. They are quite thin, so they cannot carry a large current. But that's the only solution for making such integrated module. Then you have the cadmium sulfide layer, and then the cadmium telluride layer, and then you have here back contact. Here you have a similar part with amplification of the structure. This is a thin film module, which is based on a flexible material like plastics. This has been, for example, applied to many football stadiums when the football cup in Brazil took place. The advantages: it's flexible, can be easily adapted to curved surfaces. The disadvantages: it's thin film and the efficiency is quite poor, and also the durability sometimes is quite poor due not to the solar cell but to the plastics used here. If we take a comparison between the different PV technology, for example here crystalline silicon on the left side in blue color, and some thin film technologies such as amorphous silicon, cadmium telluride, etc. So usually the crystalline silicon has the highest efficiency. There were some progress in cadmium telluride, but still the highest efficiencies occur in crystalline silicon. So they have the smallest area requirements to produce a certain power. So thin film have usually lower efficiency and require larger areas. Also, yes, this is more disadvantage. Cadmium, crystalline silicon has higher temperature coefficient. That means you have to take into consideration losses at high temperatures. As I mentioned, unfortunately, the standard test conditions are set with operation temperatures of the cell of 25 degrees, which is not realistic at all. Usually the temperature goes up to 45, 50 or even 60 degrees. So you have a considerable loss to the high operating temperatures. In thin film technology, it's usually less. Depending on the technology, they have different temperature coefficient. You remember the table I gave you in the last lecture. Concerning the spectral efficiency, crystalline silicon usually has the highest efficiency in the red part of the spectrum. So they work usually better at large AMs. It means when the sun is not shining perpendicular on them, and or AM1, usually closer to sun side. This effect is not very big. It's in the vicinity of 3%, but has to be considered if you do a calculation of large-scale PV fields and so on. Usually, especially at amorphous silicon, the highest efficiency is the blue part of the spectrum. If you go to cadmium telluride, it's more in the central part of the spectrum. So it's a little bit better for small air masses. This is only particular true. The next point, high prices, long lifetime. Okay, high prices, that's not true anymore because the prices went down a lot. And nowadays they are even in the vicinity of thin film modules. So the price difference between crystalline and thin film is very small. Nowadays, this has been different a decade ago. Long lifetime, that's still true. So many financing institutions, they only allow crystalline silicon to be applied because they have more reliable warranty and the track record is much better. And you see usually you have lower prices at thin film modules. You have a more difficult yield prediction, especially if we go to amorphous silicon because there's degradation, but also kind of anti-degradation when you heat it up. Amorphous silicon module sometimes it's getting better for a time, and so on. So this makes accurate energy yield prediction rather cumbersome. So this is some efficiency and cost trends for PV. This is not completely new, but you see here just the efficiency goes up. As I told you, nowadays we have for crystalline in the vicinity of 20%, and the costs are going down. So both ways are very good development. What has to be considered, I mentioned already. So for the yield prediction, you have to I have not a standard test conditions parameter because the indoor tests as used for the standard test condition tests do not represent the outdoor performance. As I mentioned already, there are temperature effects. There are effects due to deflection. That means non-perpendicular incidences, and the efficiency goes down at low irradiance level. And this is particularly important if you apply in Germany because we have for long periods, winter particular, this winter not, but usually we have quite low irradiance level, and there the performance and the efficiency is not the efficiency given in the standard test conditions. And there's been mentioning already spectral effects, depends on the position of the sun and the localization you put the modules in. But usually these effects are quite small, but sometimes you can gain a little bit if you consider that, and so on. So the aim is to get more the electrical energy yield in kilowatt hour per year. And because the specific energy yield, for example, if you use a 1 kilowatt power plant under standard test conditions as a reference, and you want to know if I install 1 kilowatt of a PV power plant, how much kilowatt hour of electricity does it generate per year? Well, part of my PhD thesis was to put that all into a computer program. So I made a quite extensive radiation model with the spectrum at the different part of the day, the adequate incoming, the incidence angles on the module, then the reflection on the module, not only on the surface, but also in the different layers, considering also re-reflection within the layers, interference, and the very end, I calculated the cell reaching energy flow there and the part that could be converted depending on the condition, actual condition of the solar cell. That means temperature and so on. So this is an interactive process, so you have always to keep up with the temperature. And then I could calculate the actual electricity output of this cell, which you see here in the gray zone. Here you see the crosscut of a PV module. This is what I mentioned here. There's the different reflection on the top surface, but also on the interfacing surfaces within the module, and so this part is not completely lost. It maybe re-reflected some part and then could still enter a silicon. This depends very much on the refractive index of the materials used. Some typical values are given here. There's also spectral effects of the of the optical densities here, so we calculated for every wavelength separately in order to get a very accurate representation of the cell-reaching energy flow. Here are some results on that. So this is a time of day, and what you often find in literature, just they take the first interface here, glass air as the most important interface, and they don't even consider the incidence angle. They always take a perpendicular incidence, and that's the result of it. So you find in some literature, okay, we have 4% losses only, independent of the part of the day, because it's not considered either, the incidence angle, and this is a result. And this may come to inaccurate simulations of the actual performance of the PV module. If you put it a bit more accurate and you consider the actual incidence angle of diffuse and direct irradiance, so we just made a model here, not only considering direct irradiance, but considering all, because about even at a very clear day, 30% of the incoming irradiance is diffuse irradiance. So you take a look at the sky, you see just the blue part of the spectrum, which is coming from all parts from the sky. If you have a bad day, you hardly have any direct irradiance, and all irradiance is diffuse, but comes from all directions. So this also was considered in that model, and the result you see here. So in the morning before 6 o'clock, you already have some lights. This is just basically diffuse light, and at 6 o'clock here, the sun comes up. And this is considered here because it's not perpendicular, and there's no perpendicular incidence. It's a spread, and therefore the optical performance is a bit less. You lose about 10% due to these reflections. And then sun goes up, so that means we have a very flat incidence angle and a lot of reflection. Therefore, the optical performance is decreasing. In total, you have about 20% of reflection here. And then sun is slowly going up, and so the incidence angle is getting more towards perpendicular, and the losses are less. And then at midday, we almost have, perpendicular incidence. You still see some differences here, because here's also considered the diffuse part. As I told you, this still is not always under perpendicular incidence, so there's a small difference between those two graphs. And then it's completely symmetrical. In the afternoon at sunset, then you have a lot of reflection. Then sun is down, and then after sun is below the horizon, you still have some diffuse irradiance, which is average reflectivity or transmittance, as mentioned, represented here. Then the next stage of the model is that you consider all three stages here, not only this reflection, but this reflection and this reflection. And so this is represented here, but we didn't consider dispersion. Dispersion means that the optical properties change at different wavelengths. So the optical density here, the refractive index here usually changes with the wavelengths, not so much for glass, but for silicon, this is quite significant. And due to that, the reflectivity changes also significantly, and therefore also the transmittance of the optical performance, what you see here. So here you see then if you consider the three layers, then optical performance really a bit worse than predicted, very much far away from what you often find in literature. Reflection losses are only at 4%. And if you took all modules into consideration, you come to the bold line here. And if you don't consider internal reflection, that means here, if you don't consider this re-reflection of the upper part of the modules, you underestimate the performance a little bit. It's not much, it's about 0.5%. But if you want to really be accurate, you can consider that and you arrive at line, and so you can make a very accurate prediction of the incoming energy flow on the solar cell. Here, this is the so-called weak light effect. This depends on the purity of the material, the purity or the accuracy of the processing, and the effects you say here. So we have two modules, module A and module B, and they all perform the same under standard test conditions. So that means 25 degrees of temperature and an irradiance level of 1000 watt per square meter. So here you see they perform pretty much the same. Here the efficiency of almost 15%. But if you go to lower irradiance level, then this resistance RP, remember, if you go back to the last lecture, you'll find it at the equivalent circuit here, this RP effect here. And here the RP at module A is bigger, so there's less current bypassed here, and the performance is still good, while module B has a lower RP, and therefore performance is going down. And the importance of that effect depends on the location. So for example, here you have the Brasilia, which is the capital of Brazil, with an irradiance characteristic, what you say here. So here is the frequency or the probability of such a irradiance range. So most of the irradiance in Brasilia is coming in at an irradiance level of about 800 watt per square meter. If you compare that to Frankfurt, there you see most of the irradiance comes in at about 300 watt per square meter statistically. And so you see here that, for example, if you take Frankfurt, you see the specific energy yield, as we discussed before, kilowatt hours per year per kilowatt peak installed. You see here the module A is performing slightly better, and you get 900 kilowatt hour of electricity per year per kilowatt installed. While if you choose module B, you only have, how much is it? 865 kilowatt hour per kilowatt peak installed. Another effect, what I've been already mentioning, is shadowing. Explain it here. This is, you already know, this is the interconnection of the different solar cells interconnected in series. So you have a module, and if it's fully illuminated, you have this IV curve here about where the 0 is the maximum power point. But what happens if you shadow one cell? This could be a leaf, or could even be a bad cell, or a shadow deriving from a tower or something like this. So then if you shadow one single cell, for example here cell number 1, this would be fully illuminated, and here disconsider this at the first moment. So we take a look at the IV curve, and you see here voltage stays the same, but the current is drastically reduced according to the reduced irradiance level, which is reduced by 75%. So you only have a remaining 25% of the initial current. And we also take into consideration now what happens if you apply a negative voltage on that cell. So usually you shouldn't increase there, but these solar cells are not ideal, so you have a small increase in current. And why this is important? Because if we interconnect 35 fully illuminated cell and one cell which is only illuminated by 25% in a circuit, considering also the load, then there will be negative currents. I explain you wait a minute here. So you can see it here. So here we don't have 36 cells, we only have 3 cells here. So normally, disconsider the bypass diode, please. Usually what happens here, you have first fully illuminated cells. So we have here plus minus from the first cell, plus minus from the second cell, and plus minus from the third cell. So all the voltages add up. The current is all the same. And now we have this leaf here on this cell, 75% covered. So the irradiance is drastically reduced. What happens? So this leaf, consider the most extreme case, if we cover by 100%. What happens? 100% cover means that there is no current at all anymore from that cell. So that means that's like an open circuit here. There is no current flowing anymore through that. And you can consider that as open circuit here, as I mentioned already. And then if you take a look at the voltage, these other cells are still working. There's no current, but still the voltage is applied. So you have here plus minus, and then you suddenly have a reverse voltage on that solar cell. So you have here plus in the lower part of the solar cell and minus in the upper part. And so you have a negative voltage at that solar cell, and that's important to consider. And therefore, we have to consider on the IV curve of the solar cell not only the positive part, but also the negative part. Here it's indicated, no, it's not indicated here, plus, minus, and plus here. And that's considered in the pictures before here. So here we have to consider also the negative part. And what happens if we put all the IV curves together? As you see here. So we take one sample of point here, for example, this one here for demonstration of the superposition of the voltages, because the voltages, they add up, and the current stays the same. So we have to have a parallel to the current, because the current has to stay all the same. Not parallel to the current, is a parallel to the voltage axis, and has to be at a constant current. So we take this one and this one, while the current has to be the same. We have to put a straight line through that, as you see here. So we put a straight line, and then we add up this voltage plus that voltage. So this is the position of the curve. So we have a point of the new IV curve here, and we continue that to all other points of this thin dotted line to this large dotted line, which will create then our new IV curve. And this you see here. This is the red line, is our new IV curve here, and you see here it's much smaller than the other ones, and you have a very undefined maximum power point. Maybe it's here, maybe it's here, and in total you have drastically reduced power output, only because this due to this single cell which received a lower irradiance level. But the overall performance is reduced, and it's not only if you put many modules in series, it's not only one module, maybe it's a whole PV generator that's affected by that. And if you have many modules and cells interconnected together, the voltage can be even that high, not only here minus 14 degrees or something, minus 20 volts, it could reach, the most drastic case, minus 1000 volts. And that means it could even destroy your solar cell permanently. It starts at a single point, it's called a hotspot, and then all the current goes through that one. So there starts a current flow, but while this point is very small, it starts to increase and is destroying that cell. The performance is then better because this cell is bypassed then due to the hotspot, but you don't want your modules being permanently destroyed. And this hotspot may even destroy the encapsulation, so there can be humidity entering the modules over at that cell, but later also destroying neighboring cell and reducing the lifetime of the entire module. What you can do against it, you saw it already at that picture. This is a so-called bypass diode. So you put a diode here, this so-called anti-parallel, not in parallel, but with a different direction. So the diode is looking in that direction. So here you have the cathode, and here you have the anode. The cell within the solar cell is vice versa here. And what happens, so if you have a normal conditions, take off that leaf here, then you have plus minus, plus minus, plus minus. What happens here, so we have plus here, minus here, nothing's happened to the bypass diode. If it's a good bypass diode, it's in blocking conditions and it doesn't let pass any current here. But if you come now to the bypass conditions, so we have, and not the shadowed conditions, so we have here now suddenly no current is going through here anymore, and we have here minus and plus. That means here, if you take a minus here at the cathode and plus at the anode, a current starts to flow here and bypasses that shadowed cell here. And that's the effect of a bypass diode. Usually it would be best if you would apply a bypass diode to every single cell, but it's rather expensive and the manufacturing is quite complicated. So what has been done by the industry, so they apply a bypass diode to every string or every two strings, and they put them into the terminal box. This you see here in the next lecture. Wait a minute, I can go in front of that and show it you two already, because I mentioned it already. So this is here the bypass diode, but usually this should come in the next lecture. So here is a string going off and coming back, and here you see that bypass diode. But we will go for that in the next lecture. I want to come to the exercise here. You see here. So the exercise for this fourth lecture will be you have to consider, we take a irradiance profile. Usually it's not a fixed value, it's changing every minute, but for simplification we used some fixed values. So we start before 6 o'clock, there won't be any irradiance, so 6 watt per square meter. Then from 6 a.m. to 10 a.m. we say the irradiance is constant at 300 watt per square meter, and then from 10 a.m. to 2 p.m. it reaches maximum at 600 watt per square meter. So midday minus 2 hours, plus 2 hours around midday, and then in the afternoon it starts to be reduced by 50% to 300 watt per square meter from 2 p.m. to 6 p.m. and then it's 0 watt per square meter after 6 p.m. So that's a profile, and according to that, you have to consider that in your performance of a PV module. But we have to also consider the temperature profile during that day. So before 6 a.m., we have a temperature of 20 degrees Celsius. Then temperature starts to rise. So we have, no, it's module temperature, it's not ambient temperature, actually already the module temperature. And we have here 30 degrees Celsius of the solar module inside your cell from 6 a.m. to 10 a.m. and it starts to reach its peak from 10 a.m. to 2 p.m. with 50 degrees Celsius. And then in the afternoon, while ambient temperature is also increasing, it's not the same as the morning temperature, it's a bit higher. So we have 40 degrees Celsius from 2 p.m. to sunset at 6 p.m. and then it stays at 20 degrees Celsius after 6 p.m. So first task for you is make a drawing of the irradiance and temperature curve during that day, and then you should calculate the actual generated electricity during that day for a 10 kilowatt peak. Remember, this P, index P, means that it's measured under standard test conditions of a PV power plant during that day. You should consider, because it's crystalline silicon, that the temperature coefficient here is minus 0.4% per Kelvin temperature increase. So that's a temperature increase for power output. You don't have to consider the voltage, fill factor, and the current index, so just it's already for here for power output. And then there's asked for about the performance ratio. This is the relation of the electricity being generated actually in relation to the temperature, to the irradiance, what would be generated at 25 degrees cell temperatures, such as STC conditions. So the next part of, so please do this at home. I'll present the solution of that Monday next week. So the next part is here. The fourth task is here. You should decide from which parameters depends the open circuit voltage of a solar cell, whether it depends on the spectrum of irradiance at the same level of irradiance, or whether it depends the temperature of the solar cell or the solar cell technology. It's a multiple choice question. Could be nothing could be correct, one could be correct, or even three could be correct of those. 4b is from which parameter depends the short circuit current of the solar cell. So it depends of the spectrum of the radiance and the level of the radiance. One is correct, two correct, nothing is correct. Fifth is why are solar cells interconnected in series to a solar module? Is it because to increase the current? Is it to increase the lifetime? Is it to increase the voltage? Is it to increase the PV conversion efficiency? Or is it to reduce the temperature coefficient? Sixth is if just the size of a silicon cell is increased from formerly 10 by 10 centimeters to nowadays 16 by 16 centimeters, how much is the increase of voltage of that solar cell and how much is the increase of current of that solar cell? So both relatively, no, just relatively, how much percent is it increased, or give a factor, or give both the factor and the percentage increase. So just give a list of, let's say, 3 parameters of which the open circuit voltage depends of a solar cell. The 8 is for which conditions bypass diodes are important. Is it if you have a homogeneous fork outside? Is it at high wind speed? Is it at open circuit conditions, at low operating temperature, when a cell is shadowed, or when a module is shadowed? If you have a system consisting of more than one module. How do you connect the bypass diodes? Is it either bypass diodes connected in parallel to one solar cell or a string of solar cells, or bypass diodes are connected in series to one or a string of solar cells? Then, how are the bypass diodes positions or orientated? Bypass diodes are positioned in such a way that they are in blocking conditions for the voltage of the bridge solar cells under unshadowed conditions. So just it's a normal operation of the solar cells. Or bypass diodes are positioned in such a way that they are in conducting conditions for the voltage of the bridge solar cells under the unshadowed conditions or unshaded conditions. So ninth is which components are responsible for the weak light effect. So this is the equivalent circuit, and you should here decide which components are responsible for the weak light effect. So is it the load here? Is it the RP here, or the diode, or the series resistance? What are string diodes? So our string diodes are connected in parallel to PV modules. String diodes are connected in parallel to a string of PV modules. String diodes are connected in a series of PV modules, in series to a string of modules. And string diodes block the current into a string of modules if a string is in parallel and has higher voltage than the string with the string diodes, or string diodes conduct the current into a string of modules if a string in parallel has a higher voltage than the string with the string diodes, or string diodes always cause a voltage could be both, or string diodes always cause a voltage loss due to the breakthrough voltage of the diode. I'm not sure whether we really discussed it. Maybe we leave that question open, question number 10, and maybe we discuss it after the fifth lecture. Then 11th is what are the standard test conditions. So just name the conditions, could be 1, 2, or as much as you like. And 12th is what is the fill factor of a solar module, and describe it, what it means, and maybe also you have a formula. And what does a performance ratio mean? It depends on which parameters. Either the performance ratio depends on the operating temperature, the operating performance rate depends on the angle of incidence of the sun, the performance ratio depends on the actual solar spectrum in relation to the spectral efficiency of the solar cell, and the performance parameter depends on the short circuit current under standard test conditions. Maybe we didn't consider all aspects of it, but we will discuss it on next Monday. Yeah, okay, we have already the solution. I don't want to show it before next Monday. So good luck in solving. If you have any questions, you can send me an email also. Bye-bye.